Download this code from codegive.com, link in the description below. Quantum tunneling explained. Quantum tunneling is a quantum mechanical phenomenon where a particle has a probability of passing through a potential barrier, even if its energy is less than the height of the barrier. This effect is not possible in classical physics, where a particle would need sufficient energy to overcome a barrier. Quantum tunneling is essential in various physical processes, including nuclear fusion in stars, semiconductor operation, and even in the functioning of tunnel diodes. Key concepts. 1. Wave function. In quantum mechanics, particles are described by wave functions, which provide information about the probability amplitude of a particle's position and momentum. 2. Potential barrier, a region where the potential energy is higher than the total energy of the particle. 3. Transmission coefficient, a measure of the probability of a particle tunneling through the barrier. The Schrödinger equation. The behavior of a quantum particle is governed by the time-independent Schrödinger equation. Backslash. Dash backslash frac backslash bar caret 2 m backslash frac d caret 2 backslash psi, x, dx caret 2 plus v, x, backslash psi, x, equals e backslash psi, x. Backslash. Where backslash bar backslash is the reduced Planck's constant. Backslash m backslash is the mass of the particle. Backslash v, x, backslash is the potential energy as a function of position. Backslash e backslash is the total energy of the particle. Backslash psi, x, backslash is the wave function. Example, quantum tunneling model with number pi. We can model the quantum tunneling phenomenon using Python and NumPy. We will solve the Schrödinger equation for a simple one-dimensional potential barrier. Step 1. Define parameters. We will define the parameters for our system. Mass of the particle, m. Height of the potential barrier, v0. Width of the barrier, a. Region limits, x_min, x_max. Number of points for x. Step 2. Set up the potential barrier. We can create a potential barrier using a piecewise function. Step 3. Solve the Schrödinger equation numerically. We can discretize the Schrödinger equation and solve it using a numerical method. Step 4. Plot the results. We will visualize the wave function to see the tunneling effect. Here's how you can implement this in Python using NumPy and Matplotlib. Explanation of the code. 1. Constants. We define constants such as Planck's constant, mass of the particle, height and width of the potential barrier, and the range of x. 2. Potential barrier. We create a potential barrier that is zero everywhere except within the defined width. 3. Hamiltonian matrix. We construct the Hamiltonian matrix using the discretized second derivative and the potential energy. 4. Eigenvalue problem. We solve the eigenvalue problem to find the energy levels and wave functions. 5. Normalization. Each wave function is normalized for proper probability interpretation. 6. Plotting. Finally, we plot the potential barrier and the wave functions corresponding to the lowest energy states. Conclusion. This example provides a basic introduction to quantum tunneling and its mathematical representation through the Schrödinger equation. The numerical solution illustrates how wave functions behave in the presence of a potential barrier, showcasing the phenomenon of tunneling. You can modify the parameters to explore different configurations and observe how the tunneling effect changes. Quantum tunneling is a phenomenon in quantum mechanics where a particle can pass through a potential energy barrier, even if it does not have enough energy to overcome that barrier classically. This occurs because particles at the quantum level do not have definite positions and momenta, but rather exist as wave functions that describe probabilities. Key concepts. One wave function. The state of a quantum system is described by a wave function, which gives the probability amplitude of a particle's position and momentum. 2. Potential barrier. This is a region where the potential energy is higher than the kinetic energy of the particle. Classically, the particle would not be able to pass through this region. 3. Tunneling probability. The probability of the particle tunneling through the barrier can be calculated using the properties of the wave function. Modeling quantum tunneling with Python and NumPy. We'll model quantum tunneling using the time-independent Schrödinger equation, which for a one-dimensional case can be written as backslash dash backslash frac backslash bar caret 2 m backslash frac d caret 2 backslash psi x dx caret 2 plus v x backslash psi x equals e backslash psi x backslash where backslash bar backslash is the reduced Planck's constant. Backslash m backslash is the mass of the particle. Backslash v x backslash is the potential energy as a function of position backslash x backslash e backslash is the total energy of the particle. Backslash psi x backslash is the wave function. We'll consider a simple case with a rectangular potential barrier. Step-by-step code example. 1. Define constants and parameters. 2. Define the potential barrier. 3. Set up the Schrödinger equation. 4. Solve the equation numerically. 5. Plot the results. Here's the complete code. Explanation of the code. 1. Constants and parameters. We define constants such as the reduced Planck's constant, the mass of the particle, electron, the width and height of the potential barrier, and the energy of the particle. 2. Potential barrier definition. We create a potential array where we set the potential to 0 everywhere except in the middle, where it takes the value backslash v underscore 0 backslash. 3. Hamiltonian construction. We build the Hamiltonian matrix using the finite difference method. The Hamiltonian is a tridiagonal matrix where the diagonal elements represent the kinetic and potential energy, and the off-diagonal elements account for the kinetic energy. 4. Eigenvalue problem. We use numpy.linalg.a to find the eigenvalues and eigenstates of the Hamiltonian. The eigenvalues correspond to the energy levels of the system, and the eigenstates correspond to the wave functions. 5. Plotting. Finally, we plot the probability densities of the first few wave functions along with the potential barrier. Conclusion. This tutorial provides a basic understanding of quantum tunneling and demonstrates how to model it using Python and NumPy. By adjusting parameters such as the barrier height and width, you can explore how these changes affect tunneling probabilities.